Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about one of my favorite topics called stoichiometry. The term sounds a little bit scary, and I think a lot of students look at it and get really nervous by it, but I have to say we're going to make it nice and easy, and we're going to talk about stoichiometry today in terms of s'mores. So typically this is where I like to make s'mores with you guys in the classroom, and hopefully if we make it back to school this year, we'll definitely still do this activity. S'mores are one of my favorite things. If you are not familiar with what a s'more is, it is a delicious graham cracker chocolate marshmallow sandwich. And you usually have them if you go camping, but we have made them over the Bunsen burner the past couple of years, and it's been awesome. So let's go ahead and dig right in and talk a little bit about s'mores. So a perfect s'more, at least in my opinion, and you can make various types of s'mores, is made from one whole graham cracker, right, split in half because you need the top and the bottom, a marshmallow, nice and toasted. It has to be perfectly toasted though, and 3 squares from a Hershey's chocolate bar. So we're going to create that s'more, but we're going to write it through a chemical equation. So let's go ahead and get started. Okay, so our s'more, okay, the first thing that we need to start with is a graham cracker. And so we're going to abbreviate graham cracker today as GC graham cracker. Now, do we need any subscripts here? The answer is yes. Okay, if you think about a graham cracker, it can technically be broken into 4 separate pieces, right? It comes with like those little serrated ridges in the center of it, so you can break them into smaller pieces. So we're going to call this GC4 just because one whole graham cracker can technically be broken into 4 pieces. Okay, the next component of our reaction is, or our reaction of our s'more is the chocolate bar. Okay, and the chocolate bar is again a Hershey's chocolate bar, and so we're going to abbreviate that as CH. And we need to think about what a chocolate bar consists of. Does it need to be broken, or can it be broken into smaller pieces? And the answer is yes. Okay, it can be broken into a total of 12 teeny tiny little pieces of chocolate. Okay, and then our last component of our chemical reaction or of our s'more making is going to be the marshmallow. And a marshmallow, we're going to abbreviate as big M, little m, marshmallow. And there is no subscript for marshmallow because they're singular, right? If you take a marshmallow out of a bag, that's it. It's just the marshmallow. Okay, now to create our perfect s'more, okay, we're going to essentially make this a synthesis reaction, right? We're taking all these different components and making it into one thing. And so we need only one product. And so in that one product, we need to write out how many of each we are using. So we are going to end up using all 4 pieces of that graham cracker, right? GC4. Okay, we're going to end up using the whole marshmallow, and we're going to use, if you look down again, the perfect s'more has 3 pieces of chocolate. So we're going to do CH3 and marshmallow MM. And so this is now our new chemical formula for a s'more, GC4, CH3, MM for marshmallow. Okay, now this equation isn't balanced, and we do need to balance it appropriately. So let's go ahead and balance this chemical equation. So if you look, our graham crackers are balanced, our marshmallows are balanced, okay, but our chocolate is not balanced. So in order to get that chocolate balanced, okay, we are going to go ahead and place a 4 as my coefficient in front of the s'more. This will give us a total of 12 pieces of chocolate. Okay, but in doing this, we've also made an imbalance in our marshmallows, so we need a 4 here, and we've also created an imbalance with our graham cracker, a 4 here. And so what this tells us is that for every 4 graham crackers that I have, I will need 1 chocolate bar, 4 marshmallows, and from that amount of ingredients, I'll be able to create 4 s'mores, okay? So from this piece of information, from this equation that we've just written, we can get what is called the mole-to-mole ratio. And a mole-to-mole ratio is going to be found from the coefficients of a balanced equation. Okay, and so let's go ahead and let's take some time now to come up with our mole-to-mole ratio for each of the following. So our mole-to-mole ratio for graham cracker to chocolate. So graham cracker is a 4, right? Because we get that from up here, our 4. And then our chocolate is a 1. So it's a 4-to-1 mole-to-mole ratio. What about then chocolate to marshmallow? So chocolate is again a 1 to our marshmallow, which is a 4. Why don't you go ahead, pause the video here, and try the remainder of these mole-to-mole coefficients. Welcome back. Hopefully you paused the video. So let's go ahead here and get the rest of these mole-to-mole ratios. Okay, so marshmallow to graham cracker. So if you look, this is a 4-to-4 ratio. We can reduce that though and say it's a 1-to-1 ratio. Either of those are totally acceptable. Okay, graham crackers to s'mores. Again, this is 4-to-4 or 1-to-1. And then for s'mores to marshmallows, again, 4-to-4 or 1-to-1. Okay, and again, what this says is that for every 1 marshmallow, I can create one s'more, or for every 1 graham cracker, I can create 1 s'more, or for every 1 marshmallow, I'll need 1 graham cracker, okay? So this is telling us about our relative amounts of everything that we need in order to create this s'more. Okay, so now let's get down to what is stoichiometry. So stoichiometry is just the mathematical process of using these mole-to-mole ratios from our balanced chemical equation to help us solve for specific amounts of substance, okay? In this case, we're talking about s'mores. So if our bag of marshmallows contained only 20 marshmallows, how many s'mores could we make? Now, you might look at this problem and say, well, Miss Delia, that's really simple, right? If I have 20 marshmallows, each s'more requires 1 marshmallow, and therefore I can make a total of 20 s'mores. And if you're thinking that, you're totally correct. That is the correct answer. However, I do want to show you using stoichiometry how we would get to that answer. So what we're going to do for stoichiometry is we are going to go ahead and we're going to write out our given. And we're going to be using dimensional analysis again, okay, with that mole-to-mole ratio. So we write out what we start with, which is 20 marshmallows. Okay, or I should have really abbreviated this, so we're going to abbreviate it big M, little m. Okay, and then we're going to set up our conversion factor. Now, in this instance, our conversion factor is our mole-to-mole ratio that we just talked about above. Okay, and what we're going to do is we're going to go ahead and we're going to say, okay, I am looking to determine how many s'mores I want, but I'm looking to use marshmallows to figure that out. So I need to look up the mole-to-mole ratio of s'mores to marshmallows. So looking at our balanced equation, s'mores is going to be up top. So for every 4 graham cracker, 4 chocolate, 3 or s'mores, right, I require 4 marshmallows. Okay, so this is literally all stoichiometry is utilizing this mole-to-mole ratio to help us determine how much of something that we are going to either need or create in a chemical reaction. Okay, so as always with dimensional analysis, our units cancel. Okay, and so we'll cancel this too. And so now we get 20 times 4 divided by 4, or 20 times 1, okay, is equal to 20 graham cracker, 4 chocolate, 3 or 20 s'mores. Okay, let's try another one. If I brought 18 graham crackers to class, okay, how many s'mores could I make for class? So in order to do this problem, again, we're going to write out what we start with, 18 graham cracker, GC4, okay, set up our mole-to-mole ratio from our balanced equation. Graham crackers we want to cancel, so that's going to go on the bottom, GC4. And I want s'mores up top, so GC4CH3MM. Okay, now I want to look for my mole-to-mole ratio. So I'm going to scroll back up. So I have a 4 coefficient in front of graham cracker, and I have a 4 coefficient in front of s'more. So again, this is a 4 to 4 or 1 to 1 ratio. Our units are going to cancel, and we end up with 18 times 4 over 4 or 1, giving us 18 GC4CH3MM or 18 s'mores. Okay, awesome. What I'd like to do now is I want you guys to actually go ahead and try this one on your own. So if you guys can pause the video, and I want you to determine how many chocolate bars I would need in order to make s'mores for our whole class. Okay, so let's assume that we have 33 kids in our class. Okay, and I want to know how many chocolate bars I need. So go ahead, pause the video, and when you're ready, unpause and we'll go over it. All right, welcome back. Hopefully you paused the video. If you didn't and you're just following along, that's okay too. Okay, so how many chocolate bars would I need in order to make s'mores? Well, we have 33 students, and we're going to assume we want to make a s'more for every student. So that's going to mean that we want a total of 33 GC4CH3MM, or 33 s'mores. I want to know about the number of chocolate bars that I need, and chocolate bars we represented as CH12 from our equation over the GC4CH3MM, okay? And so now I want to know how many, and I need my multiple ratio. So let's pop back up and take a look. So I have 1 CH12 for every 4 GC4CH3MMs. So 1 CH12 over every 4 GC4CH3MMs. And again, what this is saying is that I need 1 chocolate bar in order to create 4 s'mores. So if I need, 33 s'mores, how many chocolate bars is it that I need? So I'm going to go through and my units again cancel. And so now our problem just becomes 33 times 1 divided by 4. 33 times 1 divided by 4. Okay, so 33 times 1 divided by 4 is 8.25 CH12. Now, that's the exact number of chocolate bars that we would need. However, I can't buy a quarter of a chocolate bar, so I actually need 9 chocolate bars in order to create s'mores for the whole class. And I love this because this is taking a recipe essentially, right? And helping me determine how much I'm going to need in order to complete this project for our class. So if I were to try to come up with a general equation for solving what we just call mole to mole stoichiometry, which is what we just did, okay, I'm going to just go ahead and use this very general, okay, equation of our given moles, okay, and we're going to use, again, this is our mole to mole ratio, okay, so this is the mole to mole ratio from our balanced equation, okay? And we are going to put moles of desired up top, like what are we looking for, okay, over moles of given, okay? And that's going to be our very general equation for mole to mole stoichiometry. Now, as fun as this is with s'mores, and I am really looking forward to hopefully the day that we can make them together, I do want to go ahead and relate this back to an actual chemical equation and do a problem together. So let's go ahead and do this, this problem together. Okay, so here we have a word problem. Aluminum oxide is created from the reaction between aluminum and oxygen. Write the balanced equation for the formation of aluminum oxide. So aluminum is a metal, and so it exists on its own as a singular Al in a balanced equation. However, okay, oxygen is diatomic, and so we do have to account for that in our balanced equation, okay? And we're going to create aluminum oxide, which if you think about it, again, we have to crisscross. So aluminum forms a +3 charge and oxygen forms that -2. So if we criss and we cross, we get Al2O3. Okay, now this isn't balanced, so we do need to go through and balance this equation. So let's go ahead and do that. So in order to balance this, I have 3 oxygens on my product side and only 2 on my reactant side. So in order to get to a balanced equation, we need to multiply by 2 to our product side and 3 to our reactant side in order to get that 6 value. By doing that, I've now created 4 aluminums on my product side, and so I need a coefficient of 4 on my reactant side. Perfect. What type of reaction is this, and how do we know? So what type of reaction is it, and how do you know? Looking at this reaction, this is going to be considered a synthesis reaction, right? And what's our evidence that this is a synthesis reaction? Well, think about our general formula. We have A plus B becoming AB. We have 2 simple substances becoming a more complex substance. So elemental aluminum, elemental oxygen becoming aluminum oxide. Okay, cool. Now, if you start with 4 moles of aluminum, how many moles of oxygen would be required for a complete chemical reaction? So let's go ahead and set this up using stoichiometry. So I'm starting with 4 moles of aluminum, okay? And I want to know how many moles of oxygen I'm going to need. So moles desired goes up top, moles of what I'm trying to cancel goes on the bottom. And we pop back to our balanced equation and we just plug in that coefficient from our balanced equation. So for moles of oxygen, that's 3/4 moles of aluminum, and moles of Al cancel. So let's go ahead and do that. Moles Al cancel. So we get 4 times 3 divided by 4, which is going to give us a total of 3 moles of O2. Beautiful. Okay, let's try a couple more. Okay, let's try, actually, you know what? Let's try both of these, but why don't you try to pause it and see if you guys can solve these before I go over them. So let's go ahead and hit that pause button in 3, 2, 1, pause. All right, everybody, welcome back. Hopefully you paused. Again, if you didn't because you're feeling lost, it's okay. Let's go through it together. So suppose I wanted to produce 6 moles of aluminum oxide. How many moles of aluminum would be required and how many moles of oxygen would be required? So our starting point is 6 moles of Al2O3, okay, for both problems. And I want to know how much of my starting materials of both aluminum and oxygen would I need if that was the amount of substance I wanted to create. So again, we want to put moles of what we want over the top. So we're looking up top for moles of Al and on the bottom moles of O2. And in both cases, we're trying to cancel moles of Al2O3. Okay, not sure why this gave up on writing, but we'll try. There we go. Moles of Al2O3. Okay, and now we go back to our balanced equation. So our coefficients are 4 to 2 for aluminum. So 4 moles of aluminum creates 2 moles of aluminum oxide. And it's a 3 to 2 for oxygen to aluminum oxide. So 3 moles over 2 moles of Al2O3. Let's go through and cancel our units. So moles of aluminum oxide cancels. And so we end up with 2 problems. 6 times 4 gives us 24. Divided by 2 gives us 12 moles of aluminum. And 6 times 3 gives us 18. Divided by 2 gives us 9 moles of O2. And so just thinking about what this problem again is asking, if I want to create 6 moles of my product, aluminum oxide, How many moles of aluminum do I need to start with? Well, according to our mole to mole ratio, I need 12. And for oxygen, I would need 9. Okay, and that's all stoichiometry is, friends. I hope you have a great rest of your day, and I will see you guys tomorrow. Bye.